So this is a very simple random number guessing game. So we have 6 switches that we are going to use on the board as a user input. And as I would change the logic on these switches, you'll see the number being presented on the board. So the first 2 segments from the right, so my guess is the first random number, say, will be 41. And you can use these 6 switches. So essentially you have to guess a number between 0 and 63. And we have a random number generator which is going to be displayed on the 2 leftmost 7 segments by pressing a button right here. It looks like it's 32, so I am close but not close enough. I changed my logic here using switches again, and I hope that the next number that I'm guessing will be 43. I press the button. Ooh, 48. So therefore you have to just keep on pushing these switches, change the logic, and then hope that you can guess the next random number. If you want to restart the game, you can actually press this button right here. Everything actually the random number generator goes back to 0, and if you put the switches back, then you would know that everything is 0. So I am actually making I'm actually leaving a lot of room in this project for improvements, adding features, but from here on you should be able to build upon something on the same lines and make something better and an advanced version of this. So let's get started. Imagine that you have 6 D flip-flops. Since you are going to produce a 6-bit random number generator, you will provide a positive edge triggered clock to these flip-flops, a reset button which will basically set everything to 0 if the reset pin is high, and then, as you know, the way the D flip-flop works is your next state is basically what input that you have, and the output of one flip-flop becomes the input of the following flip-flop. So for example, input D goes in D flip-flop 5, D5. What comes out is Q5, and Q5 is then fed into D4, and so on. Now for a 6-bit LFSR, the data lines that are going to be tapped and then run into exclusive NOR gate will be the 6th and the 5th bit. Now according to Xilinx documentation, if you are creating a 6-bit LFSR, then you need to tap 6th and the 5th bits exclusive NOR and then fed into input D, just to avoid any repetitions while generating an LFSR. Since 6-bit is going to create random numbers in the range from 0 to 63, no random number should be repeated until all those 63 outcomes have taken place, and therefore we tap the 5th and the 6th bit of the D flip-flops in order to avoid that. And I'll leave the link in the description for that documentation from Xilinx, which is essentially this table right here. If you have a 6-bit LFSR, then you need to tap on bits 6th and 5th. Imagine that everything is 0 initially, which means all the Q5, Q4, Q3, all the Qs are 0. Hence, at the exclusive NOR gate, the inputs are 0, 0, which means the output is going to be 1. And when the positive edge of the clock arrives, all the flip-flops will be triggered, which means there is going to be a shift in the logic. Everything will move from left to right, and therefore the new logic at Q5, Q4, Q3, and so on, when the clock edge arrives, is going to be 1, 0, 0, 0, 0, which makes a code for 32. So once you basically triggers the random number generator, the first number that appears will always be 32 if everything was initialized at 0. When the next, which would mean Q4 and Q5 will still be 0, and the logic at the output of the exclusive NOR gate will be 1, and when the clock edge arrives again, everything shifts to the right. So a new set of data that appears at all the Q's will make up 110000, which is equivalent to 48 in decimal. So this is how essentially our 6-bit random number generator is going to work. We are going to create 6 D flip-flops. We are going to instantiate them. The inputs and outputs going into D flip-flops will be according to this block diagram, as you can see, where if you look at D5, the flip-flop, the output is basically the output of the exclusive NOR gate, and what comes out is then fed into D4 and so on. Correct? Before we start, I also wanted to give a quick look at the functional block diagram. So essentially you have a random number generator. You will have a clock going in, and then you have a load button. So anytime load button is pressed, a random number is going to be generated. And then you have a reset. If that's the case, random number will go to 0. You have 6 switches as well. This will take the logic from the user. So both of these random number and the data from the switches is then fed into binary to BCD. And the binary to BCD is responsible for displaying the 2 data on 2 different segments of the Basys 3 board. And as you saw, the binary, this part is actually going to generate the random number on the first 2 segments on the left on the Basys 3 board. And the binary to BCD module over here is going to display the logic from the user using the 2 segments on the right. You have a multiplexer and then selector switches, and every time whatever the logic is over here, depending upon that, it's going to allow the data from the 4 segments that we have go past this multiplexer, and then basically you will have the logic displayed on the 7th segment, right? So let's look at the source module. I'm going to start with decoder 7 segments. Pretty simple. I've done it many times. I'll leave the link for one of my video, because I don't want to go into too much detail here because I've already done it in the past. Just know that you start off with the 4 inputs, the BCD, so 4 inputs. You got 7 segments right here. You're going to use the always at block and then case statement. So it's just a bunch of cases right here. If this statement is true, means all the input, the 4-bit data is 00, then you want 0 to be displayed on the 7th segment. So everything is 0. All the segments are 0 except for G. G is gonna be off. And know that Basys 3 board 7 segment, they work on active low logic. So 0 is on, 1 is off, right? Similarly, you do it for everything from 0 to F, and then make sure to end it up by saying end case and follow it up by end. Then comes my slow clock. As I was telling you, we need to do that because this is a 100 megahertz clock frequency that's coming off from the Basys 3 board. We need to cut it down to 100 hertz. Therefore, we use a counter. So 100 hertz. In order to generate 100 hertz, if we can count up to 500,000, so that would mean 100 hertz, which will 10 millisecond frequency. If the period count is not equal to 499,999, when you do the math here, it comes down to 499,999. That would mean 5 milliseconds have not occurred, because 10 millisecond is for the whole cycle, and half a cycle would be 5 millisecond. Then the period count, basically counter, will go up by 1, and we set the logic initially to 0. Clock out is your slow clock. But if this statement is true in a sense that the count is the reason I say 499,999 is because 0 to 499,999 will make 500,000 clock cycles. So then if that's the case, you would want to set the count to reset to 0, clock goes to 1. So this is your slow clock. Again, I've done it many times. I'll leave the link in the description for the video. Just wanted to quickly go over. Then you have the binary to BCD module here. And because it's a 6-bit, so I set the input to 6-bit. You also, you don't want to, so in case, you know, I'm going to leave these lines over here in case if you have a number which is more than 6 bits, you can follow these comments over here if you like. And then I got 2 set of outputs, one for the tens, one for the ones for each random number and the user logic. Initially I create a register BCD data and assign it a value of 0. I use the always at block. Whatever is the logic, whatever is stored here, whatever is that number, that gets stored in BCD data. This binary could be coming from either using logic from the switches or from the random number generator. Once it's stored in BCD data, then I just say tens equals to BCD data divided by 10. And I say ones, which is my second output, because each number will have ones and tens. The number can go from 0 to 63. Tens would mean BCD data divided by 10. And ones would mean BCD data, whatever that number is, percentage 10. That is for the remainder. Okay. And the easier way to understand this part of the code is, imagine a random number is 50. Okay. Now tens equals to BCD data divided by 10. If number is 50, that means BCD data will get assigned a value of 50. 50 divided by 10 is 5. So tens get 5, correct? And then ones equals to BCD data remainder 10. If you divide 50 by 10, then what will be the remainder? Well, remainder is going to be 0 because it's 50 is exactly divisible by 10. And therefore you get 0 here, correct? So 5 will be displayed on tens digit, 0 will be displayed on ones digit, and therefore it makes a binary to BCD. Now if you were going to do a 12-bit say, then you would have thousands, you will have hundreds, you will have tens and ones. So if you're doing for thousands, you're going to take that number and divide it by, 100. Not divided by 100, but you're going to have to divide it by 1000 here, right? Of course we're not doing that, but in case if you have to do it, then you would do it this way. And similarly, if you are hundreds, then you have to take that data divided by 100, and so on. Anyhow, so I got 2 of those, one for the random number, one for the user logic. D flip-flop is pretty simple. Again, I have done it in the past. You get a clock, reset, load button, input D, and register Q. Q is going to hold the value, whatever is at the D, when the load button is pressed and the clock has arrived. And therefore the logic would be, whenever the positive edge of the clock arrives, if the reset pin is high, then Q gets to 0. Else, if load pin is high, then Q just simply follow D. Whatever is at the input, that gets stored in Q. I also have a debounce button here, and again, debounce just makes sure that a single pulse is generated, because I'm using push button, and the nature of the push button is mechanical. So anytime a button is pressed, it may think that button has been pressed more than once, and therefore it can skip random numbers which we don't want. So I just have this debounce button module here, and then I don't want to go through because I have a video. I'll leave the link again in the description on this. And then this is my random number generator, basically, which is an important part, the most important part of what we are doing in this project. So, and this is basically following this block diagram right here, right? So we got 6 flip-flops. So you will see these are my 6 flip-flops. Those have been instantiated. So if you look at flip-flop 0, which is the rightmost flip-flop, the input coming in to D0 is Q1. The output coming out is basically Q0. So Q1 is the input, Q0 is the output. And if you go over here, if you look at the coding right here, input is Q1, output is Q0. And just know this D flip-flop is basically essentially following the arrangement of the arguments in the way I have it assigned here in my topology here. So clock comes first, clock, reset, load, input D and output Q. So if I go to random number generator, I should have my clock first, then I got my reset, then I have my load button. Load button is basically going through debounce. So what comes out is a button underscore debounce. This is a single pulse output. When the load button is pressed, then the input is Q1 and the output is Q0. And you basically follow this block diagram to get the input output arguments for all the flip-flops. I'll just go to Q5, one more flip-flop, which is the leftmost flip-flop. The input is the exclusive NOR gate, which is basically Q5 and Q4 exclusive NORing, and the output is Q5. So if you look at D5, you got a clock, reset, you get the load button, and then you got Q5 and Q4. Actually, this is gonna be Q5 and Q4 exclusive NORing. Yes, you can assign expression like that. So Q5, Q4 exclusive NORing, comma, output, which is Q5, the output, which is Q5 here, and then follow it up by end module. And make sure I had created a random number generator output, and I'm assigning all these Q values into variable random. So R&D basically contains my random number. Okay, let's look at the top module. Top module is pretty simple, nothing complex here. You have the clock, reset, and load button. Reset would mean all the flip-flops will be set to 0. Load button would mean anytime the load button is pressed, the whatever is logic at the queues, that will be just uploaded onto the 7 segment. User also has the option to guess the number by using the switches. Finally, I got my 7 segments and the 4 enable. I declare my random number as a wire, and I try to get the value random number stored in a variable binary underscore random. So I instantiate the random number generator module. You got to make sure that this name exactly matches how it appears here, and I'm just following the topology here: clock, load, reset, random. Clock, load, reset, random. So my random number is essentially in this variable right here, binary underscore, and of course 6 bits. So I have declared the size as wire and as 6 bits. Then I need to get the logic from the user. So I create a variable user logic. Whatever is the logic at the switches gets stored in user logic. And just like I had the binary underscore random variable to get the random values, random number value, similarly I just wanted to have a binary user variable for capturing the user logic, which is basically coming off the switches. Okay, then I have all of my tens and ones for both user logic and for the random number, just like earlier I was showing you in the schematic that all the ones and tens here, they basically will be fed into these decoders, right? So I declared all of them here as wires, and then I instantiated the binary to BCD module. It basically takes the data, which is binary number. This module takes the number from the random number and then basically splits it down to tens and ones. And then binary to BCD module, this particular module takes the binary user value from the switches and then splits that into tens and ones. This data is gonna be displayed onto the first 2 segments on the left. This 2 data will be displayed on the right 2 segments. Then we have the slow clock, and then we have the 4 segments. Again, if you look at the schematic, you got the 4 segments right here from display 1, display 2, display 3, display 4. Those are fed into multiplexer. You will have to instantiate the decoder 7 segment 4 times. So if you take a look at the first one, this is the tens random number, which is going to be displayed on the leftmost segment. I use an instantiator name display 1. The input to that is the random number, tens random number, and it should be displayed on segment 1, right? Then you have the ones random number that goes to segment 2. Then you have the tens user value from the switches that goes on to segment 3. And then finally ones user value goes to segment 4. Then all I need to do is to basically use this section of my code as a, kind of like a 2x4 decoder to toggle my 7 segments. Again, by Basys 3 board has 4 segments. I label the leftmost segment as left, assigned a value using local parameter as 0, 0. Essentially these could be as states as well. Mid left and then mid right. So these are the 4 segments, and then creating a 2-bit register, and initially the state is going to be left, which means the random number tens value will be generated first onto the segment, and then you have the ones value will be here, and then tens and ones of the user value will be here. If reset, then of course everything goes to 0, so all the segments will be 0. We want to enable 4 LEDs, and therefore all 4 segments, and therefore they would display 0, 0, 0, 0 as you saw in the demo. And the next state will be left. If the present state is left, then the segment should display random number 10 segment 1, and if you recall, random number 10's value is stored in segment 1. Therefore I would just simply say segment gets the value what is at the segment 1, and then we want to make sure this is being displayed on the leftmost segment, so it's going to be on, the other 3 are going to be off. And we do that as if at a frequency of 100 Hertz, fast enough that the human eye actually cannot detect that these segments are being toggled, and they seem on at all times, which is technically not true. And then when that happens, state moves to the second LED, second 7 segment, which is my mid left. If the present state is mid left, then it should represent random ones values. If you look at random ones values, it's stored in segment 2. So segment 2 comes here, and then you have segment 3 and segment 4, which basically represents ones and tens for the user values, and make sure to end and case and follow it up by end module. So this is pretty much all what you have in the top module. Of course, we have a constant file. You got the clock at the top, you got the reset and the load button, then you have the 6 segments, and then finally you got the 4 enablers. And not to forget, we have the 6 switches which are going to be used by the user to guess the random number. I'm going to hit implementation here. All you need to do, actually, I'm going to save a little bit of time. I am going to as you can see, I ran the implementation earlier and I was able to generate the bitstream file, so I'm going to skip through synthesis, implementation, and bitstream since I've already done it. And all I need to do is program device, hit my target, upload my bitstream file, hit program, and you should be able to see the implementation of the code onto the screen. So it's a very interesting project. Again, you can add on more features. One change that I would suggest you guys doing it to this project is when you are trying to guess a number. So when you put the number through switches and then you press the button to guess the random number, so you will see whether there's a match or not, and you will keep on pressing this random number and setting the logic using the switches and try to guess the number. But what could go wrong here after a certain amount of time, when you reset and you press the button, you would know that the first number that will arrive at the random number will always be 32. If I reset and I press, it will always be 32. So it could be predictable. So what I would want you to do is, when I try to guess a number, right, and then say if I reset and then I press the random number button again, it should not display 32. Instead, it should remember its last state 32, and then it should be able to generate the next random number and not 32. Try to change that, and let me know in the comment section if you were able to do that, and how did you go about it, what kind of technique that you use, and share with us the code how you were able to achieve that. So again, what I'm trying to say is, notice here, every time I reset the project and I hit the button, the first number is 32. I reset, press the button, it's 32. I want to be able to generate a new number here anytime a reset button is pressed. The machine should be able to remember the last state of the random number and generate a different random number. Therefore, there's no repetition and it's more, unpredictable. That's what you want from a true random number. I hope you enjoyed the video. I know I went through some of the stuff fast. There are plenty of videos that I've already done in the past. I highly recommend watching those videos before watching this one. I hope you enjoyed this video, you find it helpful, and if that's the case, please consider subscribing to the channel. Till next time, good luck and enjoy your rest of the day. Bye.